Let Sn be a sequence of real numbers, and a real number L is said to be limit of the sequence if for every given epsilon greater than 0, there exists a positive integer k such that Sn minus L, modulus of Sn minus L is less than epsilon. First of all, understand it this way. What do you mean by modulus of Sn minus L less than epsilon? If you just extend this, if you write it, if you split it, we'll get it like this. L minus epsilon less than Sn less than L plus epsilon. Right? What does it mean? You see, you can call a real number L as a limit if there exists a positive integer k such that Sn minus L is less than epsilon for some epsilon greater than 0. What does it mean? You see, you have a sequence of numbers like this, S1, S2, S3. You have so many numbers. When n approaches to infinity, somewhere you will get some kth term. Let us say some sk. You will get some kth term, and all the numbers, whatever you get after this sk, if all these numbers are in between, this interval, L minus epsilon comma L plus epsilon, right? If you get some kth term like sk, after this kth term, whatever the numbers you get in this sequence, if all the numbers lie within this interval, then we say that sequence has a limit, and that is L. Understand what it is? You will get some kth term in the sequence. After this kth term, you will still get so many numbers. If all those numbers, not one or two, if every number after this kth term, if all those numbers lie in between L minus epsilon and L plus epsilon, then we say the sequence has a limit. Then we say the sequence has a limit, and that limit L, that limit is exactly L. And see, symbolically we write like this: limit n tends to infinity, Sn is equals to L. The same way of writing limit in the case of functions. But in the case of functions, that was what you call a continuous function. There it was. I mean, the domain was a set of real numbers directly, but here the domain is set of natural numbers. Remember, a clear difference is there. So there, all the functions, they were all continuous in nature, but here the domain of sequence is discrete in nature. Okay, that's one case. And when approaches to infinity, if all the numbers of the sequence are around this number L, if all the numbers in the sequence, when n approaches to infinity, if all the numbers in the sequence are around this number L, we'll take a small neighborhood of L actually. Within that neighborhood, if you find all these numbers, then we say that sequence has a limit, and it is L. And of course, we just pronounce it like this: Sn tends to L as n tends to infinity. And remember, as you know already in the case of functions, when such a limit exists, it is always unique. I mean, when n approaches to infinity, the sequence cannot go in two different directions. Either it may go towards a finite fixed value, or it may go towards what you call plus infinity or minus infinity. But when all the numbers are going to a particular value, that particular value must be unique only. So when the limit exists, that limit is always unique, right? So this is the basic idea of a limit. Now let me just show you a geometrical idea of this. Now look at this. See, we were speaking about sequences, right? We are writing them as Sn, right? Similar to Sn, here we are writing it as AK. There it was N, and here it is K. The remaining story is quite same. So similar to this, you see, we have actually, you can just assume it is 1 by 2 plus 1 by n. That is the nth term of the sequence. So here, instead of n, they have considered it as K. Understand the basic idea here. When you have a sequence, we can write all the terms of the sequence by taking different values for K. As you can see here, there are different dots. Understand, all those dots represent, all these dots represent numbers of the sequence, right? As we defined, sequence is a set of numbers, right? So these dots represents numbers in the sequence. See, there is no connection from one number to the other number, because they're all discrete in nature. Now see here, you can find two horizontal lines, green color horizontal lines here. You see, one is at 0.6 and one is at 0.4. And see here, this middle point, horizontal or orange color line, if you take that as L, and the distance here you see 0.5 to 0.6 or 0.5 to 0.4, 0.1 unit is there, you see, that distance I'm taking it as epsilon. Right? Now see what happened here, how we defined it earlier. You will find some kth term, and after that kth term, whatever the numbers you get, all those numbers lie in between L minus epsilon and L plus epsilon. Exactly here you see, look at this vertical line, just next to 10. Up to 10, you see, you will get all the numbers in blue color, and next to them, you know, there are some other color. So this K, 10th or some 11th number here, this is the kth number here, and after this, whatever the numbers you are getting in the sequence, they are all in between, you know, L minus epsilon or L plus epsilon here. They are all in between these two horizontal lines. Since after this kth term, every number in the sequence is in between L minus epsilon and L plus epsilon, we'll say this sequence has a limit. And to where, you know, where you have drawn this, where you have taken this interval L minus epsilon, L plus epsilon, it is at 0.5, you see. That's how this sequence has a limit, which is 0.5. Right? Understand, in the definition of a limit, we have discussed about some epsilon also. One may question, sir, what if I take epsilon as very huge? No, you can take it as small as possible, no problem. Even if you take it as very small, see here, this is epsilon. I'm just trying to minimize the value of epsilon. I'm just moving it down. When I move it down, you can see the distance between these two will be reduced. You can observe. Oh, wait a second, I cannot use this. Okay. Oh, something happened. Right, follow this. I'm just moving epsilon down. When I'm changing epsilon, you see the distance between these two horizontal lines is reducing. Right, they are coming closer to each other. Look at this simultaneously. Observe when these two horizontal lines are coming closer to each other. I mean, when the distance epsilon is reducing, corresponding to this epsilon, you will find a different kth number here. You see, earlier it was near to 10 actually, but now it is after 20 here. Corresponding to the size, whatever you are considering here, epsilon, corresponding to that, you will get a different kth number. See, ఇక్కడ మనం ఇంత ముందు చూడండి, epsilon కొంచెం తీసుకున్నప్పుడు అరౌండ్ 10 వచ్చింది. ఆ 10th నెంబర్ తర్వాత లేదంటే 11th నెంబర్ తర్వాత ఉన్నటువంటి నెంబర్స్ అన్ని కూడా ఈ ఇంటర్వెల్లో ఉన్నాయి. ఎల్ మైనస్ ఎప్సిలాన్, ఎల్ ప్లస్ ఎప్సిలాన్ ఇంటర్వెల్లో ఉన్నాయి. సో ఎప్పుడైతే నేను ఎప్సిలాన్ వాల్యూని బాగా తగ్గించానో, ఇక్కడ ఎప్సిలాన్ వాల్యూని తగ్గించేసాం మనం. సో దట్ చూడండి, ఇంతకుముందు 11th 12th ఉన్నటువంటి కేత్ నెంబర్ కాస్త, కేత్ టర్మ్ కాస్త ఇప్పుడు నియర్ అబౌట్ 25 దాకా వచ్చింది. సో ఆల్ ద నెంబర్స్ ఆఫ్టర్ దిస్ 25th టర్మ్ ఆర్ నౌ within the interval L minus epsilon comma L plus epsilon. Right? If I still reduce this epsilon, you can see this vertical line is moving towards, now it is nearly at 40. Now when I take this small value for epsilon, now see, after 40th term, whatever the numbers you will get in the sequence, they are all in and around what you call L minus epsilon comma, within what you call L minus epsilon and L plus epsilon. Now see here, I have taken only up to 50th term in the sequence, right? But now let me just extend it to some 100. I'm just moving this n value towards up so that you can see you'll get more number of terms in the sequence, right? I've taken it up to 100. Now see, even if I take up to 100, all the numbers after this 40th term, they're all within this particular interval only, L minus epsilon, L plus epsilon. So if I extend this up to infinity, see, still you can find all the numbers within this interval only. That's how we'll say this sequence has a limit, and that limit is exactly 0.5. Right? I hope you understood this now.